A jet engine can take ordinary air and fuel, unleash enormous energy, and turn it into a powerful stream of gas moving at incredible speed.
Welcome to the channel. In this video, we'll go inside a jet engine and discover exactly how these 4 stages create the thrust that moves an aircraft. At first, a jet engine may look extremely complicated, but its basic operation can be understood through 4 stages: intake, compression, combustion, and exhaust. Everything begins here. Huge amounts of air enter through the engine intake, where the airflow is guided smoothly toward the compressor. The air then enters the compressor. Multiple rows of rotating blades squeeze the air, dramatically increasing its pressure and temperature. Why compress the air? Because high-pressure air allows the engine to burn fuel more efficiently and release a much greater amount of energy.
The compressed air enters the combustion chamber. Here, fuel is injected, mixed with the air, and continuously burned to produce extremely hot gases.
This combustion creates high-pressure gases containing enormous amounts of energy. These gases now begin their journey through the hot section of the engine. The hot gases pass through the turbine and spin its blades at very high speed, extracting some of the energy from the expanding gases. But here comes the incredible part. The gases entering the turbine can be hotter than the temperature at which ordinary metals would melt. So why don't the blades melt? Turbine blades are made from advanced nickel-based superalloys, engineered to maintain strength and resist deformation even at extremely high temperatures. Turbine alloys contain carefully selected elements such as chromium, cobalt, aluminium, and titanium. These improve strength, oxidation resistance, and high-temperature performance. The secret is not just the chemical composition, but the microscopic structure. Special strengthening phases inside the alloy help the blade resist deformation under enormous heat and centrifugal forces. Some advanced turbine blades are manufactured as single crystals. Removing grain boundaries eliminates weak paths where high-temperature creep and cracking can begin. The metal is also protected by a ceramic thermal barrier coating. This insulating layer reduces the heat reaching the underlying superalloy, but coatings alone are not enough. Cooler compressed air from the engine is routed through tiny passages inside the turbine blades to carry heat away from the metal. Inside the blade, these passages can form complex serpentine channels. Ribs and special surfaces increase turbulence, improving heat transfer from the blade to the cooling air. Some of this cooling air escapes through tiny holes on the blade surface. This forms a thin protective film. It separates the metal from the hottest combustion gases. The blade's leading edge faces some of the most intense heating. Special internal passages and carefully positioned cooling holes protect this region from extreme thermal loads. The remarkable part is that the engine deliberately sends cooling air through the blades. This is while maintaining combustion temperatures high enough to produce enormous power and thrust. Every cooling hole, internal passage, coating, and alloy composition is carefully engineered, because even a small increase in metal temperature can dramatically reduce blade life. So turbine blades don't simply resist the heat. They survive by combining advanced materials, protective coating, carefully controlled cooling to keep the metal its safe operating range. The turbine is connected to the compressor by a shaft. The turbine's rotation is transferred back to the compressor, keeping it running continuously. After passing through the turbine, the remaining gases travel toward the exhaust nozzle, where they are accelerated to extremely high velocity. The engine accelerates air and exhaust gases backward at high speed. In reaction, the aircraft experiences a force pushing it forward. This is thrust. This principle follows Newton's third law. For every action, there is an equal and opposite reaction. The backward airflow produces forward thrust. And the process never stops. Air enters, gets compressed, fuel burns, gases spin the turbine, and the exhaust leaves the engine continuously. So the complete energy flow is simple. Intake brings in air, compression raises its pressure, combustion adds energy, and the turbine and exhaust complete the cycle. Remember the 4 stages: intake, compression, combustion, and exhaust. Together, they transform fuel energy into a high-speed airflow that produces thrust.